3D surface. And it's kind of similar to that. Yeah, it's kind of like that. Okay, so it's 11 o'clock. Just get the talk started. It's first welcome all of you here physically and also online. And it's my pleasure to introduce the speaker of the day, Professor Katharine Hunt from Department of Chemistry at MCU here. So where is actually the chemistry department? Is it closed?
It's just over there.
It's over there.
Right. Next door.
Probably can hear that.
Yeah.
She's our university distinguished professor of the chemistry, and she got her PhD in 1978 at University of Cambridge, right? And then she started as an NSF, National Science Foundation postdoc fellow at MIT between 78 and 79. And then she just joined MSU first as an assistant professor between 79 and 84, and then as associate, and then full professor started at 89 to 92. And then she's also, she was a chair between the chemistry between 98 and 2002. And then since then she is the university distinguished professor. And her interest is broad in the area of theoretical and computational chemistry. And today she will talk about apparently quantum information science. And let's welcome the speaker.
Thank you very much, Shannon. It's a real pleasure for me to have the opportunity to tell you about work that my group has been doing in quantum computation and with applications to the Bell inequalities, the CHSH inequalities, and also qubit entropy. So for starters, this is the iconic picture of the IBM quantum computer. And the other illustration is my cat. I neglected to name the cat Schrödinger, but that was an oversight. So I'd like to talk about the Bell inequalities to start. The Bell inequalities are a set of relationships that are obeyed by all classical objects, but in some cases not by quantum mechanical objects. And the reason that the Bell inequalities are so important is that if they are violated, as they are by some quantum mechanical cases, that means that no hidden variable theory can possibly be consistent with observations unless it also allows for faster than light transmission of information. So really profound implication of the Bell inequalities. That means no standard hidden variable theory can possibly remove the inconsistencies. So I wanted to present one of the approaches to the Bell inequalities was suggested by John Polkinghorne at the University of Cambridge. I had the great pleasure when I was a grad student in Cambridge of attending Polkinghorne's lectures in quantum field theory. This case is much simpler than that. We're just thinking about three measurement axes or three properties, A, B, C, and the outcome of measurement on each one has one of two possibilities that we designate by plus or minus. If we have classical objects, then they can possess values that are definite for each of the properties A, B, and C simultaneously. So we can count the numbers that have the characteristics A plus B plus and label that as N, A plus B plus. And then we know that if all of the characteristics can be determined simultaneously, the number of objects that have characteristics A plus B plus must be the sum of the number with A plus B plus C minus and A plus B plus C plus. So, elementary set theory. So we start from that relationship, and then we add to the expression on the right-hand side, going to add N of A plus B plus C plus, or n of A plus B minus C plus, and n of A minus B plus C minus. So both of those quantities must be greater than or equal to 0 because they are just numbers. They can't be negative. The issue in quantum mechanics is that in effect, some of those numbers will, in a kind of hidden way, go negative. But then the number with A plus B plus has to be less than or equal to the number with A plus B plus C plus the number with A plus B minus C plus the number with A plus B plus C minus plus the number with A minus B plus C minus. So what I've done really is just to take the A plus B plus, split them apart, and then add to them quantities that will enable me to regroup things as the number that are A plus C plus, because that is A plus C plus in both cases, and just pairing with the opposite outcomes for B, number that are B plus C minus, splitting up the B plus and the C minus and pairing them with the opposite outcomes for A. So what that means is that the number that are A plus B plus must definitely be less than or equal to the number that are A plus C plus the number that are B plus C minus. And this was an inequality was derived in a slightly different form by John Bell in the middle of the 1960s. So we suppose that a quantum spin might really possess specific projections along 3 different axes at the same time for its spin. But suppose there are hidden variables. We'd like to test the inequalities in that case. So there's still a problem of measurement, which is that you can only measure the spin along one axis at one time for a given qubit. So in order to get around that, a possibility is to entangle the spins or qubits. Although the qubits on the IBM quantum computers are superconducting transmons that have states that correspond to nonlinear oscillators, so that you can tune the pulses that are applied to the system when you're applying a gate to specifically target one transition and not the other transitions in the system. So in many ways, it functions similarly to spin qubits, although it's not really 100% equivalent to it. So in order to get around the limitation, you can only measure one property at a time. So how are you going to determine n A plus B plus? A way to do that is to entangle the spins or qubits. Bell, I think, considered the equivalent of the spin singlet state, where you're coupling spin up on one to spin down on the other. But in this case, it's a fairly simple thing with the quantum computer to create the state that is the combination up, up, plus down, down, and then normalized. The qubits significantly remain entangled in the same way along any measurement axis, because if you rotate an axis by theta in the XZ plane, use the rotation matrix around Y, then along the new axis, the wave function is still the combination of the spin projection h bar over 2, h bar over 2, and the spin projection negative h bar over 2, negative h bar over 2. So you can think of it, if you do a 90-degree rotation, as the combination right, right plus left, left, or front, front plus back, back. So the characteristic of the entanglement, the specific formation of it, remains regardless of how you're rotating the measurement axis. So this obviously relates to the Einstein-Podolsky-Rosen paper about spooky action at a distance. I had a long conversation with my program officer at NSF, who told me she really disliked the use of the term spooky action at a distance. And I pointed out to her it was a direct quotation from the Einstein-Podolsky-Rosen paper, which calmed her down a little bit. But the strange thing about the coupling is that when you have the entangled species and you separate them spatially, but you retain the entanglement, there are no interfering electromagnetic fields that could cause transitions, then if you measure the spin projection of one of the entangled particles along an arbitrary axis, the other particle will immediately be found to have the same spin projection along that axis regardless of their separation. So even if there's definitely not enough time for a photon to pass between the two locations, the second one will instantaneously collapse into the same state as the first. Well, if I were talking just to a group of chemists, I could probably get away with saying only that. But given that it's a group of physicists and everybody's familiar with special relativity, I expect that at least half the audience is thinking, wait a minute, what do you mean by simultaneous when they're separated in space? And there are some interesting things that follow from that, but I won't go into that at the moment. But in any event, the Einstein, Podolsky, and Rosen paper, I think, is remarkable in one regard, that it contains the sentence, "No reasonable definition of reality could be expected to permit this." And I thought it was very interesting. Probably Einstein is one of the few people who could get away with writing a paper where he's contemplating the definition of reality as opposed to encountering reality for what it is. So one of the questions that sometimes people ask Bell was, is this really any different from classical objects? And the specific connection that was made, the spins were paired up, down, then the outcomes of the spin projection measurements will be opposite to each other. And there was an Austrian physicist, in fact, he's still around, he's 77, still working, Reinhold Bertelsmann, who was famous for wearing mismatched socks. And so Bell wrote a paper called Bertelsmann's Socks and the Nature of Reality. And I'm sure that it's very annoying to Bertelsmann that he had a very long and distinguished career in quantum mechanics, but he's best known for wearing mismatched socks. Well, the question was, if you see Bertelsmann coming into a seminar room and you only see one of his feet and you see a sock and it's red, you know immediately the other sock is not red. So is this pairing of the spins up, down, really not just the same thing? Bell's argument is, no, it's actually totally different, because in the case of the socks, you know that there's not a flickering possibility of a change of which sock is which color. It's determined. Bertelsmann walks into the room. It's only that you don't know the outcome. Whereas in the quantum mechanical case, there are really probabilities that are underlying things. And the collapse of the wave function is the phenomenon that causes a definite outcome to be observed. But before the wave function collapses, there are only probabilities. And I should mention that as an homage to Bertelsmann, I'm currently wearing one red sock and one gray sock. So there's a paper by Brunner that I found very useful in the discussion of the Clauser-Horne-Shimony-Holt inequalities. They remark that Bell's theorem ranks among the most profound scientific discoveries ever made. And it's an interesting thing. Henry Stark said that the Bell inequalities were, in fact, the most significant scientific result of the 20th century. And if you think about all the competitors, that's a pretty dramatic statement to make. But the Bell inequalities do address the nature of reality. And they show that Einstein's discomfort with quantum mechanics just reflected, in essence, I think, an unwillingness to accept that there weren't deterministic results or underlying causes. I was sort of surprised when I was in Cambridge the first year. I was taking a couple of different courses there, and I had the first experience of actually looking at the Hamiltonian for the interaction between the measuring apparatus and the system being measured. And I suddenly realized that all that time I had been a hidden variable theory myself, because I thought that the way the probabilities were achieved was by some difference in the interaction with the measuring apparatus. And when I realized it was not at all the case, that the inherent characteristic of things was probabilistic, it was pretty dramatic. There's a place in Cambridge that's called Parker's Piece, and it's one of my favorite little sections of the city. It's just a stretch of grass, but in the middle of Parker's Piece, there's a lamppost. Parker's Piece is very close to the boundary between the city of Cambridge and the university. And someone had painted on the lamppost reality checkpoint. And I think it's an interesting question when you go past reality checkpoint, in which direction are you entering reality? But the university has my vote for reality. Well, violation of Bell inequalities, well known. It was first confirmed experimentally by Friedman and Clauser in 1972. So 50 years ago now. They studied the polarization of photons that were entangled with each other because they were created in a cascade in atomic transitions. There were some developments subsequently, and I think that probably the most interesting of the later developments was spun by Aspect, Dalibard, and Roget, and they were trying to get around one of the known loopholes in the experimental demonstration that the Bell inequalities are violated, CHSH inequalities are violated. Their thought was that you have two measuring apparati. They're separated from each other. You're going to look at the polarization of the spin of a photon at one and polarization of the spin of the photon that reaches the other. And you have many transitions going on. So you have cascades happening all the time, collecting the photons. You want to make sure that you have coincidence measurements. So you're really getting the entangled photon measurements. And then they thought, perhaps what's happening here, and this is really wild, but it's an illustration of, I think, the cleverness of people doing the experiments in detecting ways that there could be hidden variable action that they weren't taking into account. So they thought perhaps there's some communication among the photons about what measurement axis is being used at one site or the other. And so the earliest photons coming in wouldn't have that information, but as the experiment proceeds, the photons could hypothetically acquire that information. Sounds ridiculous. I can't think of any mechanism whereby that could happen, but perhaps there's something. So they came up with the idea of selecting the measurement axis while the photons were in transit. So there was not enough time for information about the direction of measurement that was being used to pass between the photons each time the photons were being detected and their spin polarization was being measured. And they chose them initially with a random number generator, I think, but subsequently fluctuations in the intensity of light from stars has been used in order to set the polarization settings on the detectors. So really wild. Alan Guth was involved in that as one of the astrophysicists that I know. A couple of other loopholes that have been closed, or at least partially closed. One of them is the coincidence loophole, and certainly everybody in this audience is expert in the issues of coincidence. You need to be certain that you're getting the photons in the pair. Another loophole is the question about the detection of all of the photons that are being transmitted. And in fact, the detection efficiency is not as high as one might like. And if you're going to come up with any possible way to get around this in the attempt to preserve hidden variable theory, one of the arguments has been that because you don't detect all the photons that you do detect follow quantum mechanics, but the photons that you don't detect have hidden variable properties. There's another loophole, which is one of my favorites, which is called the clumsiness loophole. And this is one that attributes just random error to the experimenter. That seems a little unfair to me, but this was the basis for the award of the 2022 Nobel Prize in Physics. I'm sure that you followed that with, I hope, great excitement. I was really pleased by this. I'd had some discussions with people in the main physics department here in the past who felt that the Bell inequalities were sort of obvious and not anything really important. I think if you have quantum mechanical thinking deeply embedded into your approach to things, that's probably the case, but I found them pretty startling. And I've mentioned John Clauser. I'll say a little bit more about the Clauser inequalities in a little bit. Alain Aspect is the one who did the experimental work with the entangled photons. Anton Zeilinger will come up, especially when I am talking about the n-qubit Schrödinger's cat states. The one other thing that I wanted to mention in this context is I think John Clauser is probably the patron saint of people whose H index is 25 or below, because it shows how important it's possible to be with not such a high H index. So the violations of the Bell inequalities are in fact well known, but the question that I wanted to ask was, can we see them on the noisy intermediate scale quantum devices? It was not so obvious that this would be the case. And in fact, David Merman at Cornell was arguing for slightly earlier in the development of quantum computers that the faults of the quantum computers would prevent detecting a violation of the Bell inequalities. Well, it's really, and I should mention, the Nobel Prize was 2022. We started this work in 2019. So our test on the quantum computers was ahead of that, although obviously 47 years or something behind Bell. So it's easy to create the Bell state. We just apply an H gate to a qubit in its starting state, and then we use the C0 gate to couple two qubits and immediately generate this construction. We need the probabilities of A plus B plus, A plus C plus, and B plus C plus, where we make one measurement on one qubit and the other measurement on the other qubit. So for spin correlated qubits, we have the key observables that we want to look at. And one of the characteristics, experience has shown that the fault rate for the production of the qubit state 1 is actually appreciably higher than the fault rate for the production of the qubit state 0. So one of the things that we did was to reduce errors somewhat. We looked at the combination P of A plus B plus P of A minus B minus, because that has compensating errors with the A minus and B minus production. I was talking when Dean Lee organized a seminar presentation, Charles Bennett was one of the people who zoomed into it. And I was mentioning to him that it was always harder to produce the qubit in the 1 state than the 0 state. And were there ways to get around that? He suggested that I could just relabel the qubits so that 1 became 0 and 0 became 1. That's too effective. So to test the Bell inequalities for spin-coupled qubits, what we did was to make measurements pairwise along 2 of 3 coplanar axes. So we picked axes A, B, and C and had angle theta from A to B, theta prime from B to C, and then theta plus theta prime from A to C. And we constructed a differential delta that is the difference between P of A plus B plus and A minus B minus, and then subtracted off the right-hand side of the Bell inequalities to get a quantity which should be negative all the time if the qubits behave classically, but could be positive quantum mechanically. There's still one problem that we had to deal with, which is the IBM quantum computers only permit you to measure the spin in the Z direction. And we wanted to find out about measurements along angles, not strictly vertical. So the method that we used was a fairly simple one to get around that was, we know that there's a complementarity. If you take the norm square of the inner product of 2 quantum vectors, the order of the 2 vectors doesn't matter, which means that the probability that the spin is up along an axis Z prime, if the spin is known to be up along Z, is the same as the probability that the spin is up along Z if it's known to be up along Z prime. So we have this complementarity, and that means that we can use the measurements along Z, but still get the measurements that we need, the information that we need for the tilted axis. So here are the results of our first test. This is looking at, this was IBM Burlington. So these are the results for the probability of spin up, plus the probability of spin down on IBM Burlington. This is just looking at the one side of the Bell inequalities. And I have Scooby-Doo up there from the cartoon show because he was famous for uttering ruh-roh, which means there's a problem here. And there is indeed a problem here. You can see that the results for the pi/2 pulse are pretty good. They fit the quantum mechanical prediction, which is the solid curve. But the other results are actually not in good agreement at all. Further you go away from the pi/2 pulse, the worse they get. So that's sort of a problem. And you can see I've plotted the results that we got from different numbers of shots, 1024, 4196, and 8192. The variation in the outcomes is reduced as you increase the number of shots, but the overall agreement with the quantum mechanical results is not significantly improved. So if we had only this approach to use, we would not be able to get very far in testing the Bell inequalities. There was also the question of whether we could use known error correction methods on the quantum computers. Well, at the time, the quantum computers that we were working with were all limited to 5 qubits. And if you think about the error correcting codes, Shor's method requires 7 qubits to correct 1. Steen's algorithm requires 5. That's believed to be the smallest number of qubits that you can possibly use. If you want to use a surface code, which is better for quantum error correction, it takes even more qubits. And we only had 5. Well, it reminded me a little bit of a remark that Lou Greenberg, who was one of our directors of computing on campus, made at one time, that when he started out working in computing, it was felt that if you couldn't get your entire program into 640K, you weren't a very good programmer. And I think that's kind of an incredible joke now, but obviously we need to do something here. And what we found was that if you used a filtering technique, we couldn't use quantum error correction because we didn't have enough qubits. But if we used a filtering method, then we could bring the results into much better agreement with the quantum predictions. And not only that, but the red dots are the smallest number of shots per run. The blue dots are the greatest number, and you can see that we get a convergence. The errors away from the quantum mechanical prediction tend to go away with the use of the filtering matrix. So I wanted to mention a little bit about how the filtering matrix is constructed. The basis for that is that we start out by preparing a state 0, 0, both qubits and spin 0. And then we look at the probability of outcome when we just make an immediate measurement, no gates applied to the system at all. Look at the outcomes for 0, 0, 0, 1, 1, 0, and 1, 1. And then we know if we have a state that should be 0, 0, what the combination of the faults in the interior of the quantum computer and the measurement faults are doing in producing this whole group of possible states. Then we can repeat that for the state 1, 0, 0, 1, and 1, 1, and then construct a matrix which will convert the intended input into the observed output. Inverting that matrix is a way of estimating from the observed output what the actual original input on the quantum computer was. It should reduce the measurement error, and it may compensate in part for faults interior to the computer, not just directly connected to the measurement. So we have,
account for random kind of.
it can't do that. No, it gave you, that's a really good point, because there could be processes that affect an individual run. We're taking an average. We used 25 runs of 8192 shots each to get the average effect for the filtering matrix. And it's certainly true within an individual run, there could be random effects that are not picked up or corrected by this. And that's one of the reasons why having the error correction would be much more valuable if we had not only enough qubits, but a reliable enough computer. Technically speaking, we were able to test the Shor and Steen algorithms on the IBM Melbourne computer. But if I mention Melbourne to anybody who's actually worked with the IBM systems and tried Melbourne, they know how faulty it is. It's very faulty. In fact, it's retired now. Yeah.
You do the runs without that mitigation in just the raw data. Did you run them on different machines?
No, same machine. And I was going to show one of the results here that I think is of significance. The filtering matrix actually changes fairly slowly in time. If you do the average over the large number of runs, large number of shots per run. So these are 2 runs on the Orense computer. They were taken 5 days apart. And you can see there is variation in the filtering matrix from 1 day to 5 days later. And there's certainly averaging that goes into this, but I think this is a very strong suggestion that the remaining error is systematic here. And that what we're able to correct for that effect, although we can't pick up some of the individual random variations. Oh, and that's an interesting thing too, because they recalibrate the computers normally around 7 a.m., sometimes earlier in the night than that. And if you can get your runs in right after they've recalibrated, then it's better than later. In fact, one of my students designed a program to observe when the computers were being recalibrated and immediately submit its jobs right after that. I had another experience where I was working on Vigo, and Vigo at that point had just been released from research usage by IBM, and it was in superb condition. I was getting fantastic results with just excellent agreement with the quantum mechanical output. And then I had a grant deadline coming up, so I had to go away from Vigo for a couple of weeks. When I came back, it was not performing much better than any of the other computers. So definitely they can be tuned and calibrated, and they give better results right after that.
One of the suspicions is like with the IBM machines, since you have a computational basis which is very sensitive to thermal excitations.
Yes, right. Yes, absolutely. Yes, and that's a really important point, because the computer has to be maintained at 15 millikelvin, and the operations that you perform with the gates are always perturbing the temperature. So I wanted to show a diagram for choices of theta and theta prime, where you get non-classical behavior as opposed to where you get quantum behavior. So I put in a floor in the horizontal plane that just cuts out all the regions of classical behavior so that we can focus on the places where the Bell inequalities are going to be violated. So we look at the differential theta that I defined in terms of the difference between the left-hand side, right-hand side of the Bell inequalities. We can express that in trigonometric form, and positive values are the ones where the Bell inequalities are violated. Depends on cosquared of theta over 2, cosquared of theta plus theta prime over 2, and sine squared of theta over 2, theta prime over 2. So these are the results from the IBM quantum simulator. Quantum simulator works really nicely. The only problem is it's truly a classical computer. It's just simulating what the quantum output should be. But you can get an idea, because we're using 8192 shots per run, you can get an idea of the magnitude of the random error that's just purely statistical error in the calculations. the way that we arranged it, we used 10 runs at each of the angles theta, theta prime, and theta plus theta prime. And then we combined them in all possible combinations. So we had 1,000 different combinations overall. The error bars that are shown go 1 standard deviation above and below the average values. So this is what you get with an error matrix that takes the filtering into account. Examine delta. These are the actual experimental results. This is on IBM London mostly. The red and the green are on IBM London. The purple is IBM Melbourne. IBM Melbourne was really attractive because at the time it had 15 qubits available. But the problem was that IBM Melbourne fulfilled David Merman's worst nightmare, that you couldn't really see the violation of Bell inequalities on that computer due to the fault level. You can see that actually classical behavior is within 1 standard deviation of the outcomes on Melbourne. So as far as that computer goes, the deviation from hidden variable approaches can't be detected. But on the other hand, the raw results from IBM London are in red, much better computer at the time. And then with the filtering matrix, the results are in green. The solid curve is the quantum mechanical results. So I think we have a level of agreement that shows that even with the noise level and the fault level of quantum computers in 2020, we could get pretty good agreement with quantum mechanics to make them potentially useful quantum mechanically. So then I wanted to talk a bit about the Clauser-Horne-Shimony-Holt inequality. This differs from the Bell inequalities in that it applies to the correlation functions of the, sure, yeah.
Do you actually explain a little more about, because I think the filtering is mostly about correcting the measurement error.
Yeah.
What is the measurement error? What do you mean by measurement error?
Well, what has to be done in the quantum computer is that a pulse is applied, and it actually lasts for a fairly long length of time. The pulse lasts for multiple microseconds, whereas the gates are usually, in the diagrams that I've seen, the gates last maybe 20 or 25% of the length of the measurement pulse. The measurement pulse is intended to determine whether the system that's the transmon qubit is in the ground state or in the excited state by inducing a transition between the states. And why that is subject to error, I think one of the possibilities is that the transmon qubits have states that correspond to nonlinear oscillators. And so the excitation may not necessarily go exclusively to the first excited state, but there'll be, even though there's non-resonant behavior, there'll be some excitation into higher levels. Also, I think grouped into measurement error are some of the intrinsic errors within the quantum computer before you even perform the measurement. So there's crosstalk among the qubits, and there can be stray electromagnetic fields inside the computer. If the temperature is different from 15 millikelvin, then you have thermal excitation in the system. So there are a lot of sources of difficulty. We see also that the pulses, if they're trying to accomplish a rotation, are excellent for pi/2, but not so good for the others. So a lot of that all gets grouped into measurement error when it really shouldn't be attributed just to the measurement step itself. So Clauser-Horne-Shimony-Holt inequality. This is for correlation functions of the spin projections rather than the probabilities, but really the basis of the inequalities is the same. What I worked with was a 3-axis version of the CHSH inequality. When the experiments were done, there were 4 different axes, and so we had 2 observers, each using 2 measurement axes, but none of them identical to each other. In the case that I looked at, I used 3 axes, A, B, and C, And the first sigma refers to the spin projection for qubit 1, second one for qubit 2. So the sigma B is measurements on qubit 1 and qubit 2, but both along the B direction. Question, I think, comes up, how can we treat non-locality? Because I don't actually know how far apart the qubits are, and the gates last a pretty long time. And so it's very probable that light could pass from one qubit to another in the course of the measurement process. So I've used a definition of non-locality that seemed sensible to me. It comes from the paper by Brunner that I mentioned earlier on. The idea is that you suppose that hidden variables that are represented by lambda might affect the outcome of the measurements that are being made by the two observers. So the definition they use for locality is that if you have some hidden variables lambda, the probability of average sigma j, sigma k splits into the probability just for observer 1 of sigma j contingent on the hidden variable, and the probability of sigma k for observer 2, again, contingent on the hidden variable. And then they take into account the possibility that lambda itself might vary between the runs. The hidden variables have a normalized probability distribution. And so the probability for sigma j, sigma k can be written as an integral over the whole range of the unknown hidden variables. But the feature is that the probabilities within it factorize into probabilities for qubit 1 and qubit 2. And that's the essence of non-locality in this context. There are other loopholes that might need to be gotten around, but those go into the specification of constraints on the hidden variables. So these are the results for the CHSH inequality on the IBM computers. And again, the red are the raw results. Anything above 2 in this particular case is a violation of the inequality. So it shows that classical behavior just is not observed. So raw results in red and the error mitigated results in blue, in green, sorry, then the quantum prediction, quantum curve, the solid curve in blue. So I wanted to take a few minutes to talk about another interesting phenomenon in quantum computing, and that has to do with the entropies of n-qubit Schrödinger's cat states. My graduate student, Nathan Jansen, took a lot of the lead in this work, but also I had a set of other collaborators. So 3-qubit example of this. This is spins up, 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 and down, 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 normalized wave function. There are 2 types of entropy that we could consider here, in fact, 3 really, but one of them is the Shannon entropy of the measurement outcomes. So make a measurement on the system and see what the effective entropy is. Another one is the von Neumann entropy that we get from the density matrix. So I wanted to show that the cat states are, again, fairly simple to construct, but there are multiple options for their construction. So in one case, we use a kind of construction that we refer to as stairstep algorithm, where we link qubit 0 to qubit 1, and then qubit 1 to qubit 2, qubit 2 to qubit 3, and so forth with C0 gates to produce the cat state. The other one we called a harpsichord diagram, where we linked qubit 0 to qubit 1, 0 to 2, 0 to 3, and so forth, linked everything by C0 gates to qubit 0. One of the surprising features to me for this was that when you run them through the quantum computer and the quantum computer does the transpilation, the stairstep algorithm always comes out the same. But even within an individual run, because you can have up to 75 circuits per run, you find that the transpilation can be different within a single run for the harpsichord algorithm. And it tends to take more gates to accomplish. So Shannon entropy of measurement outcomes take the negative of the sum over j of pj log base 2 of pj. Advantage of being log base 2 is that the interpretation is very intuitive. If the n-qubit cat state could be produced and measured with no faults, then the measurement should yield just either 0000 or 1111 exclusively, equal probabilities, no other outcomes. That would give S equals 1 independent of the number of qubits. So this is what it really looks like. This is the Shannon entropy of measurement outcomes as a function of the number of qubits in the cat state. Stairstep algorithm results from the IBM computers, Yorktown, Belém, Manila, Athens, and Santiago. The interesting feature here is that in practically every case, the curve of the entropy versus the number of qubits looks linear. It should be 1 independent of the number of qubits, but it's not. So model for the near linearity of S, we wanted to explain how this could happen. And so this is probably the simplest way of accounting for that near linearity roughly. We suppose that there's an effective accuracy A for the production and measurement of the state 0, and similarly B for the production and measurement of state 1. And then we can determine what the probability of having an outcome where you have n qubits altogether and q of them are in state 0, but the probability of that actually is given these inherent faults in the production. Then we calculate the Shannon entropy of the measurement outcomes. And this model actually does quite well at predicting the near linear behavior. It's not quite linear. IBM Q Melbourne is, as I mentioned, the faultiest of the computers that we worked with, but it had a lot of qubits, so that was useful. And both algorithms and the model that we came up with that's pretty undetailed model. It doesn't take into account the specific errors in the C0 gates, doesn't take into account the variation from qubit to qubit, but it does pretty well at predicting that this plot will be linear, more or less. Overall behavior looks like this. The entropy, if you have 4 qubits, if the error in the production is such that you have actually an equal probability of getting up or down when you're trying to code for up, then you get the maximum possible entropy, and the maximum entropy is equal to the number of qubits for each of the n-qubit cases. I think the most important observation out of this is that the slope of S actually varies among quantum computers, and it is different for computers that have the same quantum volume. Quantum volume is the thing that's normally used as an indicator of the quality of the quantum computer. But the slope of the entropy will differentiate among computers. And you can see for Melbourne, the slope of S 0.7315, completely faulty quantum computer, that slope would be 1. But Santiago is quite good. The slope is about 1/5 roughly of the Melbourne slope. We also constructed a quantum volume that's specific to the cat states and determined that by measurements. Often the quantum volume that's specific to the cat states agrees with the general quantum volume, but not always. So sure. That's an interesting question, and we didn't actually look at that. But that's obviously something that we should look at and see what happens with us. We've been exploring the entropy in a process where we're using adiabatic quantum computing to go from a set of qubits that are all spin polarized in the x direction to a cat state. And in that case, we can monitor the Shannon entropy as we go along the process. And we observe that if we have very short time steps in the adiabatic quantum computing, we get much closer to 1 as the outcome of the Shannon entropy than here. But we haven't combined that with the filtering matrix, and that's a really good idea. So this is just showing the von Neumann entropy. We have some limits on the von Neumann entropy because if you're doing quantum tomography, you need 3 gates per qubit to determine, or you need to apply 3 gates per qubit to determine the state of the density matrix. And 3 to the n, if n is 5, is not problematic. But if you go to one of the 53 qubit machines, suddenly the length of time that is taken, it's like the person who asked to be compensated by the king by placing 1 penny on 1 square of a chessboard one day, and then 2 the next day, and then 4 the next day. Pretty soon you're talking 10 to the more than 100 years at current rates for the computation. So current and future interests, I just mentioned these briefly. Adiabatic quantum computing, obviously. One of my other quantum mechanical interests ties in with differentiating the adiabatic and non-adiabatic response of a system to a perturbation. I'll mention the approximate qubit cloning also, because there is a no cloning theorem in quantum computation that says you cannot produce the state of an unknown qubit. But there's some work by Buzek and Hillary that shows that you can, in fact, produce a state of a qubit with an average accuracy that's a square root of 5/6, which is really very high. And I'm interested in the implications of that. So some of the other topics are there that I'm interested in. I just show the people who did a lot of this work along with me. Nathan Jansen, my grad student, who did a lot of the calculations on the Shannon entropy and the von Neumann entropy. He's continuing with the adiabatic quantum computing, and he's got about 3 other projects that are percolating at the same time. The other people on this slide were all high school students or recent high school graduates when they worked with me. And in my entire career prior to this, I'd had only 1 high school student who ever was a co-author on a publication. But most of these students now have been co-authors. I had 4 students in quantum computing for the summer in 2019, and I went through spin physics with them. We covered the chapter, I think it's chapter 12 in Merzbacher's Quantum Mechanics on Spin Physics, and they understood it. And then the next summer, they worked on the test of the Bell inequalities. Another group worked on the quantum entropy for the cat states. And then finally, I have a couple of people that I haven't co-published with yet, but they were working on Shor's algorithm for factorization of integers into primes. These are some of the people from other parts of my group. Some of them have left me now. Anirban left in the spring to go to UCSF, San Francisco, and he's a research scientist there. Evangelos just got tenure at Auburn, so he's a fairly recent graduate. Xiaoping is here in information technology, systems analyst, one of my really outstanding students. Nathan, really the bulwark of my group. I have what's called a working retirement appointment now. And I just also wanted to be sure to thank the funders of this research and my research in non-adiabatic processes and experimental collaborators for the projects in that area. And I'd like to thank you very much for being here and for your attention. I really appreciate the opportunity to talk about this work. Thank you.
Any questions from the audience here? Any questions online? Anyone?
Yeah.
I have perhaps a naive question. I don't know much about quantum computing. Everything I know a little bit more than in the summer school this year. The matrix that you were using to filter things, is that related to the zero noise extrapolation error correction in any way, or I'm interpreting that in a wrong way?
What it does, I think, is pick up on average what the errors in the production and reporting of a state are. And the error correction methods actually fix the qubit in a sense by having replicas of it and then detecting problems with the identity of the qubit. So that's a much stronger method of error correction, but it does, as I said, require more qubits. I just, this last summer, I received a supplement to my NSF grant that gives us $10,000 worth of computing on Cloud Bank. And one of the things that I'm really excited about, combination of things, we can use machines that have many more qubits than have been accessible to us so far. And then the other thing is that Amazon Web Services have photonic quantum computers. And I'm really interested in trying those out because we've just been using the IBM hardware so far.
So have you thought about putting up some kind of scoreboards for different machines available right now?
Yeah,
Public,
right.
incentive?
Yeah, general public, I think, has now access to quantum computers with 7 qubits through IBM. That's a totally free account. And there is some priority queuing now, but they have a level of access that's researcher access. And with those, I don't think you can get much above the 7 anyway. However, if you're paying for it, then you can get access to quite a few additional computers. I think the largest that I've seen on IBM's site is 124 qubits. Obviously, the engineering problems multiply as you go to more qubits. And Melbourne was a great idea in principle because of having the large number of qubits, relatively speaking, when it was introduced, but the fault level was much higher. I think probably crosstalk among the qubits is one of the problems. And then every gate, every time that you make a measurement, you probably transfer some energy. And there's actually an interesting issue with the von Neumann entropy. The von Neumann entropy is based on the density matrix. And so you're taking a rho log rho construction. The thing about the von Neumann entropy is that that's the one that's identical to the thermodynamic entropy. And the von Neumann entropy is also a really good measure of the error rate in the adiabatic quantum computing process, because you should be starting out in a pure state. And if you truly evolve adiabatically, you continue to be in a pure state throughout. And so the von Neumann entropy should be 0 throughout the process. Of course, it isn't. But I think that the errors in the von Neumann entropy may be connected to the heat generation in the gate processes because of its direct tie to the thermodynamic entropy.
It seems that the results just visually, even after filtering, still have some systematic deviation.
I think that's right. Yes, and especially it's puzzling to me, but the things that are hardest for the IBM computer to replicate accurately are the rotations by angles closest to 0 and closest to 180. And that's not intuitive to me, but that is how it works out.
So no more questions. Thanks for speaking.
Yeah, thank you.